Okay. Go over the homework. So if you come across a question and you don't understand how it was done, we'll go through that math together. So don't hesitate to like, hey, bro, how'd you do that? Okay. Question number one, a 22 microfarad capacitor is in parallel with a 0.1 microfarad and a 300,000 picofarad capacitor. What is the total capacitance? 0.62 microfarads? Yeah, okay. So when you have parallel capacitance, how do we treat that? So it's like a resistor, but it's opposite. So if they're parallel, all we're doing is adding them together. Okay. So what were they? 0.22 microfarad,
0.10, 300.
0.1 microfarad, and 300,000 pico. So if it's me, I'm writing all these out. 0.22 microfarad would be 0.0000022, right? Correct me if I'm wrong, because this is confusing for me too.
Yeah, micro 6.
So
right?
this is milli,
Milli.
micro, and then this would be pico.
Okay, yeah.
So 0.1 microfarad would be 0.0000001. 300,000 pico would be 0.00, wouldn't it be 3? 300,000 pico. So this would be 1,000, 300,000 be right here.
Yeah.
Would be 0.3 micro. Right?
Once you get to the number, to read like the number, you have to count backwards, right?
Yeah. So a number that looks like this, 0.0000000000001 equals 1 picofarad, right? If you had 300,000 of those, if you had 100,000 would be moving the decimal place. Bloop, right there. Right? Anyway, that's how I look at it. Add all those together and you end up with 0.00000620000. That's the same as saying 620,000 picofarads or what was it? Microfarads is 0.62 microfarads. Make sense?
Yeah.
What's up, bro? Oh, you know. If you had a 10 micro and a 15 micro in parallel, total capacitance equals parallel, so we're just adding them. So this would be 25 microfarads. Four and a 6 in series. How do you do that?
I don't understand that one. Because I know that say the plate gets and then together the plate gets the stick.
Say that again. The plate in between.
Yeah,
Okay, so that's talking about how you could increase or decrease the capacitance of that capacitor. Okay, so if I built a capacitor The same way as I built another one, but this one had a bigger plate area between it, you're increasing the capacitance. Or by decreasing the distance between the two dielectrics, you can make that capacitance bigger. This one's saying that, this one has nothing to do with the plate size or the distance. It's just saying, I have a 4 microfarad capacitor and a 6 microfarad capacitor, and they're in series with each other. Okay, so this last example was all 3 of these capacitors in parallel. So that would look like this. You understand the difference between series and parallel, right? Multiple current paths. All right, so this next example is saying, now I got now I have 2 capacitors in series. And they are 4 and 6. I had the same circuit, but these were resistors. So if this was 4 ohms and this was 6 ohms, what would the total resistance be? 10. Since these are capacitors, we have to do the product sum formula, right? The same way we would do resistors in parallel, we're going to solve this. So it would be 4 times 6 divided by 4 plus 6 would be 24 divided by 10 equals 2.4 microfarads. Right? Capacitor consists of a conductor between 2 insulators. Is that true or false? Why? Right. Rating that specifies the maximum potential difference that can be applied across the plates without puncturing a dielectric is voltage rating. A charge or discharge current flows through the conducting wires to the plates, but not through the dielectric. Capacitance increases with which one? Right. So that's the example that I just gave. I have 2 capacitors I build the same way, but one of them, I increase the size of the plate and I move the distance. If I smush that, make that plate thinner, so the distance between the 2 conductors is shorter, then I increase the capacitance. It's able to store more charge. Is capacitance the ability of a dielectric to hold or store an electric charge? Yeah, yeah, sure enough. Is charging a capacitor, does that involve the voltage source redistributing some electrons from one side of the capacitor to the other? Yeah. Yeah, okay. Components made to provide a specified amount of capacitance, what is that called? Ooh, don't read too much into that one. That was an easy one. Connecting capacitances in series is equivalent to, we connect them in series, are we increasing or decreasing the overall capacitance? Right, so it'd be the same as increasing the thickness of the dielectric. If they're in series, the overall capacitance becomes, I don't know what we just said, but less than the individual amounts. Right? Just like this example. We have 4 and we have 6, we put them in series and the total capacitance actually goes down. So the same thing is increasing the thickness of the dielectric. You're making the distance between the two conductors further, so you're decreasing the total capacitance. Dielectric strength is the ability of a dielectric to withstand a potential difference without arcing across the insulator. Yeah, I'd say so. How many storage cells can be manufactured on a chip of silicon? Kind of crazy, isn't it? You guys will be into solid state probably next spring. If you're in industrial electrical, if you're industrial maintenance, you won't take solid state, but it's kind of mind-boggling to me that solid state uses the same principles as capacitors, but like your cell phone has millions, if not billions, of little transistors in there. Like, okay, what's one of the main applications of a capacitor? Right. Because once you get up to a certain voltage, like that's all it can take, right? And in the reverse polarity, capacitor ain't gonna work. Oh. Right? No, I had it backwards. One of the most common and widely used storage cells is the dynamic storage cell that uses capacitor. 1 picofarad equals 10 to the what? Minus 12.
Well,
Where did I put that? Didn't I just write that down somewhere? Oh, I erased it. So 1 picofarad would be like this guy right here. 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
it's another number after people, right?
Smaller than pico? Yeah, I don't know. Should we come up with a name for it? Like,
Yeah.
hope this doesn't bring up a porn site. Zepto. Even smaller, 10 to the minus 15 is femto. Then you got atto, zepto, yocto, and then holy cow. Yeah, we don't need, I don't expect you to remember those because I won't remember those. What are we doing? 17? Capacitance, ability to store charge is capacitance. The action of neutralizing the charge by connecting a conducting path across the dielectric is discharging. By the way, if you're ever in a scenario where you have big capacitors in something like an old light fixture or a variable frequency drive, like you'll see upstairs in the drives classes, those things hold charge. It's like a battery, right? If you don't discharge them and you touch them, you're going to get walloped by whatever voltage is being put on them. So to discharge them, you take a screwdriver or something across the two terminals.
They do work like a battery wheel for the moment. And then the start they start recharging at some point. Once you cut the connection, you cut the recharge a bit.
It's basically a battery. Basically, yeah. But it's a controlled battery. if that makes any
Yeah.
sense. Like it's built to serve a purpose of charging and discharging at a certain capacitance. Whereas a battery, you want to get the most amp hours or how else to put it, out of the battery.
The battery, they have the charge to disconnect one terminal to the other one without any resistance, right?
To discharge a battery?
Yeah.
Yeah,
They charge right to it. Similar.
same thing.
Same thing.
Capacitor has opposite charges because of the electrostatic induction by the electrical field. That's true. I'm not sure why I kept that answer in there. It's kind of a dumb question, but the charge and discharge current of a capacitor flows. Can you read that? Whoa. Through the dielectric, to and from the capacitor plates. Through the dielectric only until the plates are charged. Through the dielectric from one plate to another. Nope. You don't ever want current flowing through the dielectric. That's the voltage rating, right? That's why we have voltage rating. You go above the voltage rating, it'll compromise you're putting too much force on those two sides. If you picture like, I don't really know how else to explain it, but to draw it, but you've got two conductors storing charge, plus and the minus, and in between there's that dielectric separating them. Okay, you don't ever want voltage going from one side to the other. That would destroy the capacitor. So you're never going to have current flowing from one through the dielectric to the other. Equivalent capacitance of 30 and 20 in series. No. Remember, we're in series. So the total is going to be less than the individual. So in that case, what did it say? 30 and 10? Or 20 and 10? 30 and 20? So it'd be 30 times 20.
Series, right? Not parallel. Yeah.
Series.
Okay.
30 times 20 divided by 30 plus 20. You're left, what is it, 12? Most important property of a capacitor is its ability to do what?
Look at DC. Wow. 590.
Mhm. The result of a larger plate area is less charge stored for the same applied voltage, which means capacitance is small. That's false. Larger plate area means greater capacitance. What is the unit for capacitance? For farad. The ability of a man, there's a lot of questions on here. I'm sorry about that. Ability of a dielectric to hold or store an electric charge is its capacitance. What is the ability of a dielectric to withstand a potential difference without arcing across the? Didn't we already have this? No. Yeah. That's probably a good thing, right? Other than being a waste of time. What is this one? Dielectric strength. 1 coulomb is stored in a dielectric with a potential difference of 1 volt. The capacitance is 1 farad. 1 circuit's total capacitance is equal to the sum of the individual capacitances. The capacitance are parallel. Yeah. Which of the following factors affect capacitance? All of them. Which type of capacitor would explode if the polarity of the voltage across its plates is reversed? We should find some and explode them. Okay, questions on the homework? Really, the key, I think, is to remember the whole parallel versus series thing. Okay. And I think the next chapter, we're going to get into something called capacitive reactance. It involves formulas and a lot of math. But stick with your bra here, and we'll be just fine. If there are no questions, we'll plan on doing the quiz on Tuesday. Let's just, for the time being, plan on coming into class every day. Okay? Because I want to make sure we stay caught up on the labs. I'm not the type to like, let's work until 2 in the afternoon on this one lab. Like, that's just too much to me. That's why we broke down the first lab into 2 parts. But at the same time, I don't want to get so far ahead in the book work that we're going back to work on previous concepts in the lab. So we'll just plan on coming in every day, doing a little bit of lab work after the book work, and at least for the time being, hopefully we can stay caught up on stuff. All right, well, do y'all have your labs from Tuesday? Yeah, hi. All right. One thing I wanted to show you guys before we get started, at least one person had this happen to where they hooked the leads up backwards, so they changed the polarity of the connection. I just want to show you what that does. Hopefully it'll make you a little more familiar with what we're dealing with here. I have my power supply at 1 volt DC. And I hook my scope up to basically color for color, so positive to positive. negative to negative, and I'm at 1 volt per division. If I hook up plus 1 volt to this thing, what will happen to the red line?
That's one.
It'll go up 1 division, correct? If I have it hooked up backwards, it'll go down. That's a negative voltage, right? All it has to do is direction of charge. If I'm putting force on the circuit one way versus force on the circuit the opposite way. Let me do that.
So if you in a positive, the positive used to be a positive voltage, right? If you positive negative, it used to be negative voltage.
Right. So for example, I'm on negative to negative and positive to positive. Right. So when I turn channel 1 on, you should see that line go up. See it happen?
Yeah.
What if I move the vertical position of channel 1 down? I think one thing that was sort of confusing you all is you tend to think visually, I at least tend to think that this little emboldened middle line is 0.
Yeah.
You're zeroing that line wherever you want to. Okay. The only point of moving this up and down is that so when you apply a voltage to it, you can see it on the screen. Right. But if I move it down here, it's still going to go up 1 division because I'm putting 1 volt on it. See that? Now if I switch them, basically I'm putting my my common on the positive part of the probe. And I'm applying a positive voltage to the ground or to the common reference. If I just switch the polarity, I turn this on, I should see it go bloop, down, bloop. Okay, so it's important to know what your polarity is. And that's just for DC voltage. In the second part of this lab, we're going to apply an AC sine wave to it using our function generator. So we're going to start to create alternating voltages and look at them on the scope. Let's do that now. By now you should have table 15-1 filled out. And number 4, before viewing AC signals, it's a good idea to check the probe compensation for your oscilloscope. Check the probe compensation, set the volts per division control to 0.1 volts per division. So how many millivolts would that be? 0.1 volts is how many millivolts? 100 millivolts. What's up, Corey? Are you high? Okay, so the first part is I just changed volts per division to 1 millivolt on channel 1. Got it, Chris? You on it? Chris just wants on the payroll. He wants to be a lab assistant. Good. Now I have to get my fat butt out of this chair. eBay. How are you today? Good. You guys done messing around yet? We've got very important AC sine wave work. Got some stuff happening? Okay. 1.1 volts per division. Set the AC ground DC coupling control to DC. I'm still on DC from the other day. Set the seconds per division control to 2 milliseconds per division. So on mine, I'm still on this guy right here, so it's still DC coupling. And then how many milliseconds per division? 2 milliseconds per division. So that's this knob here. This one. I'm at 100 microseconds and we want 2 milliseconds. Is that right? 2.0 milliseconds. Cuts the probe tip to the probe compensation connector.
What's the millisecond?
2 milliseconds per division. Did you get it? Touch probe to the probe compensation schmear. Nothing. You a square wave? Oh, there we go. Oh, I put it on the wrong one. Is that what you're seeing? weird smear.
What case will we use for the? health one?
All I'm doing is the positive lead on the top part. Should be 5 volts at 1 kilohertz. Anyway, are y'all seeing the same thing I am or no? This weird looking square wave. What are you seeing? You are, Kevin? Oh, you can't see it on there. If necessary, adjust the compensation to achieve a good square wave. I don't even know how to do that on this scope. Probe. Change that. I want to change that. Yeah. Okay. Well, no matter what you're seeing, we're just going to go with it. Because we're really bad electricians. Number 5, set the function generator for an AC waveform with a frequency of 1 kilohertz. This is your function. Oh, this is your function generator. Turn that bad boy on. Now I'm just going to find my channel 1 probes here. What'd you do? You just turned it on?
Yeah.
Hit it with a hammer. Yes. I'm gonna give you this other one, just in case I gave you the same one back. But from it. Start yelling at me again. What is it? Try using that one. Third one. Five. Yeah, I haven't even got that front. What are we doing? Set the function generator for an AC waveform with a frequency of 1 kilohertz. Adjust the amplitude of the function generator for 1 volt RMS as read on your digital multimeter. Okay, so we got a sine wave, we got 4 volts peak to peak. So we need to set it to 1 volt RMS. And what is our frequency? 1 kilohertz, and that's what I'm at already. Are you guys at 1 kilohertz? Right here. Okay. So 4 volts peak to peak. And I'm not sure. We're gonna have to see if we can even read 1,000 hertz on this thing, but we can try, I guess. All right, so what I'm doing now is I'm taking my output channel 1, so that's this guy, right? I unplugged channel 2 because I'm not using it. I don't want to get confused. And I'm at 4 volts peak to peak. Oh, no, I'm not. Wait a minute. I'm at 1 kilohertz, and then how do you change the freaking amplitude on this thing? Oh, frequency, period, amplitude. Oh, baby, oh, baby. 1 volt RMS. So I'm going to hook my meter up to, let's see, this would be
1 volt 68.
volts AC. So on my meter, I'm on volts AC. And okay, this is current. High sense, 1,000 volts max, so I guess I don't need to change those. I just need to be set to AC voltage. And I'm gonna connect these two straight up to my probe. Just color for color. So if I'm at, let's see. If I'm at 4 volts peak to peak, what would my RMS be? I guess I don't need to worry about that now. Let's just find 1 volt AC. That's pretty darn close. 1 volt, I'm at 1.06 volts AC. This is the RMS voltage. And on my function generator, I'm at 3 volts peak to peak and at 1 kilohertz.
That's 3 volt 68.
That's what my amplitude happens to be on here so that I get 1 volt AC. Is there a way to fine tune the amplitude? Ooh, I see. Okay, all right. Dang, this is sweet. All right. So on your amplitude on your function generator, oh, it's not what I want. I could read it a little better. Right now, my meter is saying 1.003 volts. And the first thing I did was got to, I think it was 3 volts peak to peak. And I'll go back to that so you can see what I'm doing. Okay, so I'm at 3 volts peak to peak. Now I'm reading 1.06 volts AC. Now I need to fine tune this thing to get closer to exactly 1 volt AC. So to do that, underneath the knob where you adjust the amplitude, I'm hitting these arrows. When I hit those arrows, it'll change from this to this decimal, right? So I go over here and take this to 2.9. That gets me a little closer to 1.00 volts AC on my meter. Then I'm going to go to the second decimal and go down to 2.8. That is freaking sweet. So where I found my happy ground is at 2.822 volts peak to peak. On my meter, I've got 1.00013 volts. Everybody with me? On your function generator, are you using channel 1? Okay, did you hit the output button? What's your frequency? Are you at 1.00000 kilohertz? What do you guys do?
Anybody else? None. Oh. I think so. I don't know. I don't know. That's your, yeah, here. You want. Here. Period, we want 1 millisecond. Frequency. Frequency, 1 kilohertz, you're out. Channel one very formula. 1 kilohertz, that's good with both 4 volt peak to peak. 1.4 volt. Now we start to mess with it. 4 volt peak to peak, we're gonna start to dial that down. That's where you start playing with this number, you should get it really close to it. Yeah, you were in channel 2, and you were also you were in period for 3. Everybody on the same page now? Need some more breakfast. Water lab, we've got basically threw number 4 out the window. And we're doing adjust the amplitude of a 1 volt RMS as read on your digital multimeter. Set the seconds per division control to 0.2 milliseconds division. So that's going to be on your scope. So on the scope, let me see where we're at. I'm on this part here. Set the seconds per division control to 0.2 milliseconds per division. And volts per division to 0.5 volts per division. Now I'm going over to my scope. Seconds per division to 0.2 milliseconds. So that's going to be right here, and this dial here. On the lab, it says 0.2 milliseconds per division. So I'm at 200 microseconds per division. Is the same as 2 milliseconds, 0.2 milliseconds, right? Adjust the volts per division to 0.5. So right now I'm at 100 millivolt. I'm at 100 millivolts, and I want to be at 0.5 volts. I want to be at 500 millivolts, correct? $500 millivolts per division. $500 millivolts per division, and I'm at 200 microseconds per division. Connect the scope probe and its ground to the function generator. Yes, sir. So here's my channel 1 scope probe. And I'm gonna take this function generator probes. I'm gonna go positive. This is my function generator. This is my scope, positive to positive, and common to ground. Ooh, look at that. We got a sine wave. Whoop, whoop. Who's excited? Yeah, we keep it connected to the. One. We keep it connected to the. Yeah, take your multimeter probes off. We're done with that. And take your function generator probes and hook it straight up to the scope probe. All right, who's not seeing sine wave? All right, here you come. A minute, need some more breakfast. You can work at all you want, but until I do it up there, I don't know what to talk about. It's helpful. See, I can take over your computer screen so you can see that right in front of you. You can probably see everything better. And you're not going to use the computer at the same time. Would it be helpful if I blew that up right in front of your face on the computer? Yeah. Yeah, okay. All right, you got me logged in. I'm happy to do that. That's me. You go away. Hello? Hey, say hello to my AC theory class. Everybody say hi to Ed. Hi. Yeah. I call you back later. All right, brother. All right, I'll call you in a little bit. Hi. Are you okay? You know what? Oh, okay. All right. You scared the crap out of me. Okay. You know what you just texted me? Was it a typo or you said I'm in the van on the way to the hospital? Yeah. Okay. I forgot about. All right, yeah, I completely forgot about the test. So okay. All right. Okay. All right. I'm still in class, but it freaked me out. So all right. You gonna say hi to my class? Everybody say hi. Say hi, milady. Now I got one taker for the milady. All right. All right. All right. Glad you're alive. Okay. Love you too. Bye. What are we doing? Everybody good? In this part? Yeah? Can we take over your computer screen? eBay, you good? No. Well, what do you want? Find out everything. The 200 millivolts, right? No, five. We want to do that. 2 milliseconds. Change that to 200 microseconds. Yep. 200 nanoseconds. 2 microseconds. That's it. That's 200 microseconds. Be at half a volt per division, so that'd be 500 millivolts. That's your function generator. Film waveform 1 kilohertz. Run over 2. Put on. Looky there. All right, I'm hijacking your computers. Well, yeah, if I just come around and do your lab for you, everybody's gonna be happy, right? What am I doing? Oh. Watch this. You see my screen? You see that better than you could on the screen up front? All right, the problem is I can't do both at the same time. So if this is better, we'll go with this. All right, connect the scope, blah, 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 adjust the vertical position control and the trigger level to control for a stable display near the center of the screen. So I'm going to change the vertical position, bring that sine wave up so I can see it all on the screen. Ah! The French just happened. Yeah, what just happened? What the? You all see what I see? You do? Anybody not have this going on? Because I'll make the rounds again. I don't care. It's my job. If you don't have this going on, speak now or forever hold your peace. Okay. You should observe approximately 2 cycles of, how do I lose my place so quickly? You should observe approximately 2 cycles of an AC waveform with a peak-to-peak amplitude of 2.8 volts. Okay, well here, let's do this. I'm going to show you what it means by 2 cycles. Starting at this point, going up and back down is 1 cycle, or the alternation. Remember the alternation? So that is 1 cycle. That is another cycle. So we're seeing more than 2 cycles on the screen. Okay. Peak to peak amplitude. How do we read that? Let me show you what I'm going to do. I'm going to move this down so this lower peak is right on the dotted line. I'm going to adjust my vertical position so that goes down to there. Now I'm going to count my divisions. 1, 2, 3, 4, 5 point. 5.24, 5.65, no, correct? Yeah, 5.7. 5.7. So 5.7 times a half a volt is what? Five point 7. That's divisions. I think it's actually 5.75. 5.75 times how many volts is it? A half a volt, 500 millivolts, right? It says it right here. So times 0.5, 2.875. So in the lab, exactly what's going on. You should observe approximately 2 cycles, yep, with a peak-to-peak amplitude of 2.8 volts. This represents 1 volt RMS. Remember, we read that with our bench meter, as shown in figure 15-3. And here's an example of what you should be seeing. Use the digital multimeter to set the function generator amplitude To each value listed in table 15-2, repeat the AC voltage measurement as outlined in step 5. The first line of the table has been filled. Remember, to obtain accurate readings with the oscilloscope, you should select the volts per division setting that gives several divisions of the deflection on the screen. Okay, so let's look at the second one, and then you should be able to do all of these now on your own. The first one is the example we just did. It's already filled out. Okay, so 2.2 volts RMS, and let's go ahead and put our bench meter on there at the same time. We're not using the DC power supply, so I'm going to turn that off. I'm going to hook my meter, which is this guy, up to the connections that I already have. So here's my negative, my positive. There's my 1 volt RMS. Now the next line tells me, well, let's set it to 2.2 volts RMS. Okay. So on my function generator, I want to be on amplitude. I'm going to adjust this dial. I'm going to go over to adjust it to, what am I doing, 2.2 volts RMS. So that's somewhere around 6 point something. All right, so I'm at 6.205 volts peak to peak here, 2.2 volts RMS. And this is what my waveform looks like. So now I need to make adjustments on the scope so I can see that whole waveform on the screen. Which knob on the scope do I need to make adjustments to? Volts per division. I'm going to turn that down. Boom. I got 2 cycles and I can see the top and the bottom peaks. So now I'm at 1 volt per division. I need to adjust the vertical position so my bottom peak gets onto one of the lines. Right there. And now I can measure up divisions. 1, 2, 3, 4, 5, 6.2. 6.2 divisions times 1 volt per division is 6.2 volts peak to peak. Everybody good? Everybody happy? No? What do you Zoom in on my, that question. What that you want Yeah, so when you make your adjustments to your voltage over here, you've got, your settings are all the same, we're just gonna change this, the voltage division like you did. What you wanna see is the biggest amount peak to peak you can while it's still in the screen. Sure, two waveforms, yeah, I mean, you can change that, but you're still gonna read the same amount. You know what I mean? Okay. That makes sense. I thought it wouldn't be changed. Yep, I'm gonna zoom in on my scope here for a second. Hopefully this makes sense. First thing, when we're counting divisions, does it make sense to everybody that, you know, I've adjusted my vertical position, so I'm sitting on one of the lines in the lower peak? Yeah. Right now, I'm at 1 volt per division, which means that the space from here to here is 1 volt. If I count up 1, 2, 3, 4, 5, 6.2 divisions, that's 6.2 volts peak to peak. Do you understand how I'm getting the 0.2? Each of these divisions has 1, 2, 3, 4 little hash marks in between. So if you think about it, that would represent, if one block is 1 volt or 1 division, this would represent 0.2, 0.4, 0.6, 0.8, 1 division, right? So I'm reading up 1, 2, 3, 4, 5, 6.2 divisions. I happen to be set on 1 volt per division. Now, Lewis's question is, do I need to mess with the seconds per division this way to get the sine wave to do that? Or do I have to have 1 or 2 cycles in there? You can read the same thing if I change my seconds per division to that, it's fine. I'm gonna read the same amplitude. Okay, it might actually even become a little more clear. But it's gonna read the same amplitude. As long as you have a peak on the bottom and a peak on the top to read, you're fine. Okay. So when you're done filling out that table, you can answer the review questions and turn them in to me either before you leave, or you can take them home, do the questions, and bring them in on Tuesday, however you want to do it. I don't care. Just turn them in whenever you get them done.